Okay, let's begin. We don't want to make it too long. Today we have the pleasure to have in this Innovate talks, GSD talks, to Hanif, that I think that 99% of you know him. He's teaching here as an associate professor in practice. No? And Daniel Lopez-Perez, that 70% will know you because you've been at the GSD for many years. He was TAing me and Farsid, and also I met him in Princeton. He's an assistant professor of architectural design in San Diego, in the University of San Diego now, and he has a PhD, a recent PhD finished in Princeton. And both of them have been dealing these last years with reviewing Buckminster Fuller in a different way. I would say in a way with his eyes that are very technical, but with their eyes too, and with other techniques and other knowledge. And I think that is an homage in many ways, an homage to Bucky Fuller, but also a kind of testing the geometrical and the performative response that he was really dealing with. And this, their research is much more complex, but I think that they will resume in these two aspects, the structural performance and the geometric, let's say, patterns, in a way in an attempt to systematize the knowledge and the legacy of Buckminster Fuller. So thank you for coming, and thank you, Daniel, for coming from San Diego, and Hanif for coming. So please. Can we switch off the lights?
Okay, so thank you, Naki and Hanif for inviting me here. Today we're celebrating the 120th anniversary. Oh, can you hear me? Yeah. All right. So I'll try to speak to the mic. So today thank you everybody to join us. Today we're celebrating the 120th anniversary of Fuller's birth, and it's very exciting for me to return to the GSD. Today, before Hanif, I'll be introducing some of Fuller's concepts historically and showing some of the documentation of our project, the Spherical Atlas, which is a research project with my students at the University of San Diego, which is on its 6th year, and of course in conversation and collaboration with Hanif. In fact, some of our students are here. They've moved on. Now they're in the master's program here in Princeton. Thank you for joining us too. So, of course, Fuller is mostly known for his design of geodesic domes artifacts, which in the feature of time were described to say covered the most amount of square foot than any other shelter. In parallel, Fuller also pursued the writing of many, many patents, inventions that sought to define the intelligence of these artifacts, but now universally. As the synthesis between the specific intelligence of these artifacts, and if you will, the patterns, the physical pattern of these artifacts, and the universal knowledge base created by the patents, by the inventions, or if you will, his conceptual thinking, three concepts emerge in Fuller's pattern thinking: the Dymaxion, Geodesic, and Tensegrity. These concepts are, of course, research projects that tackle broader questions. So the project of cartography, Fuller is, of course, concerned with resolving the projective problems of the Mercator, but also tracing relationships between land masses and available resources and inequity. It starts out with a cartographic question and then moves to a very charged political question. In the project of the geoscopes, these relationships now turn three-dimensional to model ambiguously the sphere. And finally, with the concept of tensegrity and the jitterbug transformation, the analogies deepen to embody in Fuller's mind the foundation of nature and the universe. Fuller's pattern thinking is literally developed across time through drawings and endless drawings of patterns
that span, again, from the two-dimensional to the three-dimensional, two-dimensional questions of cartography and their translation into three-dimensional geodesic relationships. Once in 3 dimensions, the geodesic lines offer an infinite amount of arrays of patterns and subdivisions. And as it was described by K. Michael Hayes when he picked this very early sketch of Fuller, Fuller's geodesic patterns are not just lines, but rather vectors of force. And I quote, "an empirical systems of differential relationships that create and organizes times, movements, trajectories, and ultimately sensations." As such, Fuller's pattern thinking then moves on to the 4th dimension with the concept of tensegrity and what he called the jitterbug transformation. So if the whole, as Hayes shows us, if the whole is fluid, so is the part, so is the cell. Joachim Krauss describes this transition as Fuller's challenge to a fixed Cartesian system, a quest for a geometry that models nature herself. If the cuboctahedron unit results from the thickest packing of spheres, which we see on the left around a nucleus, in 1948, Fuller's modeling brings out the fluid relationship of the Platonic bodies in a new light as dynamic phase transitions, a process where the jitterbug transformation oscillates, expanding and contracting. And here's the sketch where this cell expands, contracts, and becomes tetrahedrons, octahedrons, icosahedrons, and again ends at the cuboctahedrons. He calls this discovery the jitterbug, which was a kind of 1940s dance, where I guess bodies are in constant state of transformation. So let me take a moment and go through these very fast and then move on to the Atlas. Dymaxion, of course, is the synthesis between dynamic and maximum. Maximum output, minimum input in terms of technology. Find the most efficient, literally the most efficient lines in the map. This starts out as the Dymaxion map, which is a pattern that we know. And Fuller's obsession with deducing planarity out of curved surfaces with the least amount of distortions was more than cartographic. I mean, this image, for me, is very emblematic of wanting to understand one's relationship to the environment, one's relationship to the Earth. If we are able to understand our environment, and we can reframe our relationship to it. Once the cartography is divided into an atlas system of variable subdivision and aggregation, all kinds of combinations emerge, and it unleashes many readings and many continuities and discontinuities, which have all kinds of alternative readings. Finding continuities over land or across oceans, and the dramatic political implications that this brings. And of course, energy consumption and resource inequities. What amount of energy is consumed by certain parts of the pattern and not others, and how to make that more equitable. By the start of the 1970s, Fuller's world game begins to project some of these patterns, speed them up, slow them down, and brings historical patterns with projections of future patterns, with what he calls a powerful IBM machine projecting on it. In terms of geodesics, now we move on to the three-dimensional, the transition from two-dimensional to three-dimensional, and Fuller builds a number of geoscopes, spheres that are unambiguously modeled on the Earth. I'm only going to speak about one in Princeton in 1960. The Daily Prehistorian at that time hailed it the best globe map ever built, a cartographic achievement where architects could project data upon it and through having resolved the distortions of the Mercator, get a more accurate image of our relationship to the globe. Of course, powered by IBM machines and LED lights. Once in place, the system would allow for simulation, speeding up, slowing down. But as it was built by students, there was an unexpected last-minute accident in which the structure ended up being on the exterior and the membrane displaying the map being bended up on the interior. Of course, Fuller is an extraordinary optimist, and he said, this accident made me realize, in his writings, he writes about this, that actually both projects are one. Right? The cartographic project, the geoscope project, and the geodesic project. he described how unexpectedly these two were married. In terms of the tensegrity, now moving on to the cell, we see how Fuller moves on to the fourth dimension and the concept of tensegrity. Of course, tensegrity is a structural system based on tensional integrity with tension members holding together rigid members. For Fuller, tensegrity is also the structural basis of nature, where he claims famously nothing in the universe touches. These are, in fact, lines of force. And I quote, "Nature has compression operating in little remotely positioned islands as high energy concentrations such as the Earth and other planets at the macrocosm, and island electrons or protons or other atomic nuclear components in the microcosm. The universe is a tensegrity. Tensional lines becoming lines of force." In this sense, the lines of tensegrity are self-similar and scale infinitely up or down, and Fuller, in his own slides, follows these patterns in nature, tracing, for instance, magnified images of the structure of the eyes, cornea, or what he calls the tensegrity geodesic triangulation in the human testes. So, moving on to our project, the Spherical Atlas research, of course, the challenge here was to categorize Fuller's vast production of geodesic forms historically, but also generatively. How do we learn from this intelligence? How do we continue to build upon its intelligence? How do we apply this knowledge? And now we see it in a new light. If in fact it is true that all the polyhedrons are related because they're phase transitions of one another, then that means their grids of subdivision are related, and that means all of these forms are related. So what we have on the one hand is geometry, and then what we have on the other hand is the physical world. So we started to divide these two and started to trace the path from the polyhedron all the way to each individual prototype, going through what polyhedral solids, what grids of subdivisions, what structural systems, from strut to plate to tensegrity, and then ending up on the prototypes. This is historically. And physically, of course, we weigh these things, all of them aiming to do the most with the least, the lightest possible across strut and cable surface models. But most importantly, also what we were after is formal and structural systems open to transformation. We understand these as systems that continue, that have the capacity to continue to grow in intelligence. Fuller astonishingly only uses 6 out of the 19 polyhedral solids to project his entire geodesic work. So discovering these unprecedented combinations, adding dashed lines to the existing map was as important as the historical project. In this process, we followed 2 different methodologies. One is a top-down methodology in the process of categorization, definition, and transformation, in which we determine the geometry, right? What is the projected geometry? What are its foundations? And then we followed a parallel process, a bottom-up reconstruction, almost like kind of an archaeological reconstruction of these as physical artifacts. So in terms of the top-down process, we started out by writing a parametric definition to control not only the accuracy of the original geometry, but also the capacity to have levers that gives us the possibility of transformation. In this process, we start by studying the 19 Platonic, Archimedean, and Catalan solids, polyhedral, and their duals, and begin to think about these polyhedrals at first, like Fuller did. He was experimenting with the closest packing of spheres, and in this transformation, so in the transformation from a cuboctahedron to an icosahedron, he removes the sphere in the middle. And this model, if I had it in physical form, spins a little bit, right? So in this initial spin, by removing the center sphere, is where he comes up with the jitterbug. The jitterbug transformation, the capacity for a cuboctahedron to be transformed into an icosahedron. We, of course, do not follow the model of the spheres, but follow these later models where it is the vertices along the edges that are moving. and following this transformation. And we move from a cuboctahedron, icosahedron, from an icosahedron to an octahedron, from an octahedron to a tetrahedron. And this is a very famous movie in which he shows time and time again, even to children, how the model is no longer packing of spheres, but it's the vertices moving, right, to transition from one shape to the next. Of course, the simple stick model brought us into a parametric definition with 45 steps. That took us more than a year and almost killed a couple of my students. And but it is important to understand these things as phase transitions of one another. Writing the definition allows us to go from to change that inscribed polyhedron, right? And if we only use the 6, but imagine it expanding to other solids beyond polyhedron. After the inscription, we have subdivision of the polyhedral faces. So each of the faces Fuller divides into an order. He establishes 3 families of grids. And as he rotates the grids, class 1, class 2, and then class 3, you have different relationships between the subdivision and the edge. Sometimes they're aligned with the edge, sometimes they're misaligned with the edge, and sometimes the rotation is absolutely aleatory. After subdivision, we get rate of subdivision. What is the amount of subdivision that a single polyhedron phase can have? And we range from 2V, 3V, 16V. And here we see the different grids in their families following their rotation. So class 1, class 2, class 3 on the axis. And we see where his models fell, so we only see they populate very few. He rarely used aleatory rotations on his grid. The definition expands to include subdivision and then projection. So once we've subdivided the polyhedral phase, we project it onto the surface of a sphere. Projection could happen to a sphere, but it could also happen to any. In fact, Fuller has an alternative entire universe on space-time structures that are projected to a plane. So here we see how the polyhedral are interconnected and projected. And we see the different grids. So class 1 grid, how it now becomes the spherical surfaces has different rates of subdivision. We see the same grid but with a different solid. This is with an octahedron inscribed, and then with different rates of rotation. Each of these are different. The intricacy of all these grids is different. Class 2 grid, which now begins to center of be bespoke around the center line and different rates of subdivision. In class 2, with a dual, now he's using a rhombic trioctahedron, which is the only dual that he uses, and gives him a base unit that is different. Third class, this is the grid that he never used. It's a kind of aleatory grid where the grid rotates. It's not aligned either to the edges or to the center line. And that has a rate of subdivision. So I'm just going to see if this works. So this is a, oh, 1 second. I'm just going to put, I need to put this in front of your screen, sorry. Okay. So this is a very short, but it's a very short video where you see the full transition. You see the definition working with the levers to transition across all polyhedra. And then we see projection onto the surface of a sphere across all polyhedral. And with the levers, we're able now to control it. Rotation, which sets up the different families, and then rate of subdivision, which scales up and down. And at the last minute, we realized that this is isotropic. It's in every phase. Every phase is the same. Okay, so now I have to find out how to get rid of this. Okay. Sorry. All right. Okay, and then there are a number of other grids which he studies, which he calls spinning grids. 31 circles, 21 circles, and these are primitive grids before he gets to inscribe. And as we move backwards, obviously, they're the basis of the cartography pattern. In terms of the bottom-up digital reconstruction and transformation, this was really like going into an archaeological dig. Fuller never draws, I mean, it would be useless to draw elevations and plans, right? Because these things are more complex than that. So he only draws parts and instructions, parts as they relate to the whole. And in this case, these are the two drawings that then produce this prototype. And we follow its geometry, we follow how it relates to the polyhedron, and then how it's open for transformation, so changing the inscribed solid from within. University of Minnesota dome, now mixing tensile members with rigid members. And then once you have the definition, you're able to change the inscribed solid and get different continuities or discontinuities. Some of these models are, of course, closer to the geodesic geometry, and some of them are forced to span out inscribed onto different solids. The magnesium geodesic hanger dome has the capacity to then build up hierarchy. So we start to manipulate the sections of the struts. Then he starts to mix hybrid systems, in which he makes strut systems with catenary, what he calls catenary domes, with membranes. And this produces a geometry that's a little bit further away than the geodesic geometry. And of course, changing the rate of subdivision has dramatic impacts. So we are at each instance running experiments. Then he moves on to a number of systems that are based on surface. The fly's eye dome, fiberglass with channels, and in itself has the capacity with the same geometry and the same solid to be reconstructed with prefabricated reinforced concrete. So that it manifests itself differently. And of course, the geometry changes as it's forced to be thick and be precasted and be joined and so on. And then we have other kinds of models that are more focused on surface, like the fly dome model. These are the only drawings he gives, the instructions for this, and reconstructing it in terms of what is the inscribed solid, what's the rate of subdivision, and how are we able to create transformation. Surface models then bend in his laminar geodesic system and become everything from aluminum sheets, fiberglass, to corrugated cardboard. So these things have a discussion with their material manifestation at every instance, and they bend. Jacob, I think you modeled this one. They bend in different ways with different axes, creating a huge amount of difference and transformation. We have other models where the piece is only this bit. This is the only piece that constitutes his dome de Triennale, which is made out of corrugated cardboard. And again, uses a dual inscribed and then the geometry and the tensegrity models. So let me close and turn over the floor to Hanif. But this summer we were invited at the U.S. Pavilion at Venice Biennale to reflect upon variations and what is this knowledge base today. How do these patterns, how does this continue to be expanded? And I asked my research team to trace pattern variations every year since the day he passed. 1984 to 1914, we managed to find pattern variations every single year, and some years they were upwards of 30 or 40 pattern variations. And what do we find? Stirs, we find some of them closer to his original geodesic structures, others depart from it. Everything from maps to foldable, collapsible tents, to floating islands, to entire schematics for catamaran ships, to ring strengthening structures, all the way to greenhouses, kites. We saw a guitar there. These range every year. So structures that build up artificial reefs, suspension, you name it, even stadium structures. Yeah. So let me turn over the floor to Hanif. Thank you.
Maybe I think so while we switch over, can I just say that I'm mostly a structural engineer and I'm mostly a practitioner, so I don't have a big story on this. It's a small one. The beginning should be that it always feels like a Star Trek convention. So I'm almost as convinced as Daniel about most of this. I noticed a number of you are taking pictures and videos. Could I please ask you not to do that in my case? For reasons that will become very apparent. There's some things in here that I'm going to show that are not for general knowledge, frankly, and confidential actually. So if I could please request you don't do that. So in reaction to Daniel, where do I pick up the story? We met many years back and he sold us the whole idea. So as a structural engineer, after many years of being inspired by not just Buckminster, but all of these great thinkers, it was a fantastic opening for us because somebody here that could actually inspire us again, much younger than me, but actually to rethink the way we might test what he did. So all I'm going to try and show you very quickly is from taking it from the conversation of all the deep work, what can a convergent discipline like a structural engineer do to this great thinking? Particularly when you know there's 120 years of him, but it is probably the most tested human being in our world, in architecture, because there's so many different types. That's the one thing that is frightening about it. So to make some sense, the big thing that has happened clearly is the brute force of processing power with intuition. And that's the bit, obviously, that we could add. And there's nothing new that I'm going to show you, but I imagine that he didn't know some of these things, as in Fuller, though Daniel's students pick it up very quickly. So the way we started thinking about it was really narrow it right down. What could we model? What is a sample test we could do? We took a scale. Do you mind not taking a picture, please? If you don't mind, it's okay. Scale. Then we would pick a surface division, just pick one of, in this case, a 3V triangular truncated grid, and then give it some material. So steel seemed to be the quite common thing, and some geometry of partial dome. So setting up a sample, let's say, for a test. And then the modeling approach, what he couldn't do and what we can do mostly is we can make things visible, so things that he couldn't see. And even to set up something as primitive as that, barring the spelling mistake, we set up a modeling approach where we were looking in parallel for one sample with the intention of then growing that sample automatically in the future when somebody funds us. So one day we're going to try and do as much as Daniel has done, but just to show you what is possible, you could set an automated process that could do all of this work in time. We've tested a shell and a frame structure, and then for a certain number of load cases, local pressures, global loads, thermal loads, wind pressure, and asymmetry. And then the normal question about linear versus nonlinear analysis, which gets a bit techie, but effectively what that means is geometry changes, and taking advantage of the changed geometry in his work would also, as you load it up, is something we can do today through nonlinear analysis. Of course, there's the more fancy or more weapons grade analysis that we have to do now with flutter, waves, seismic forces, and so on. So there's a whole series of things we could set up. We set a very, very basic sample up of the scale that I showed you a minute ago, and you probably can't read it, but we tested that, and we are intending as a goal for the project to take this to some real case conditions. So beyond testing this, how can we refer it to the future? What is the future use of these things? What is the current use? That's where we're taking it, as well as trying to support Daniel's endeavor in trying to get this stuff out in the air and remind people that very little in this world is new. So those kind of tests were done with both the shell and the line structure, just to show you very quickly with different load conditions, and I'm not going to go through each load case because I know I have 8 minutes, I think. The radome, we tested that. What did we learn? the sort of things you start to learn very quickly, and it becomes visible now, is that there's an enormous amount of redundancy in everything he did. So whilst he talked about less is more, frankly, most of the work he did was too much. We could take 50% out of it today. So that's the one thing we learned. We learned also that he tended to think that everything was heavenly, and loads have come to you in a heavenly way, equally distributed. What he never kind of thought about is asymmetry. So, for example, wind only acts in one direction at any one time. That creates a certain redundancy, but it also misbehaves in terms of the formal structure analysis. So you have to either change material, grid, or subdivision instead of using the repetitive model for this kind of condition. We get forensic with it, so I didn't want to just show you the samples of the global analysis, but actually getting further in. And what you start to see as you get very, very local with load types and analysis is how it behaves depending on where it touches the ground. It needs, as it turns this particular dome, as it turns from a vertical into a dome shape, and as it gets closer to the ground, obviously the loads are all getting into the ground. So there's a whole band of hierarchy of structural systems, yet most people tend to model him with everything the same. So there's a hierarchical problem that comes out of this, and then the second aspect of that is the line versus the surface. What we found between the two is even the surface structures always behave as lines because of the nature of the geometry. So at the end of the day, most of the surface structures are even more redundant because they only provide a secondary structural system. All its surfaces that I showed you very quickly in those movies were coming out very similar. I'll show you how we measure what I'm telling you. So this is not just all made up. There's an empirical measurement out of it. We also find that when you do a sample test on a local loading condition, how does it behave? So, just a patch load on it. You find the nodes being designed for that particular patch load, and they're extremely heavy. They introduce a certain complexity compared to distributed loads or horizontal loads. And that demonstrates, so making it a little bit visible for you, the bottom left-hand corner is just a load being applied at one particular point to demonstrate what happens to the elements nearest to it, and then how it tapers off in terms of axial forces, tension forces, compression forces, and right down to the ground. So we can do all of that forensically, and one of the things we found is the bottom, the boundary condition, was always underestimated as soon as you cut any one of his surfaces. We find there's a significant misbehavior at the boundary, not just in a panel and the element, so we needed to make it out of a different material or stronger, but also in terms of the deflection criteria. So for the same load, it seemed to deflect a lot more at the bottom. And then we haven't gone this far yet, but I just wanted to show you where we're headed. We've got real projects where we're looking at the second order effect and even the third order effects of wind velocity and so on. And this is the part where I wanted to not record too much. SGH structures in Boston, courtesy of them, I got these slides, which is probably one of my favorites, Epcot. And I just wanted to bring it because of the work. Some of the people that did this are still alive. And one of the things about it was that he always looked also, or at least they interpreted that one of the benefits of Fuller was in the way we construct things. So there was less human endeavor in the construction process because there's a lot more prefabrication, you can assemble things quicker. So there is something to take into the future. Okay, we're looking at robots now to do that work, and therefore there must be a moment that he saw that we didn't see yet, and now we begin to see the benefits of that. So what do I mean by that? Measuring it for real then, okay? For real, I just want to show you two very quick projects. The 2022 World Cup in Doha. We're doing doing a couple of the stadiums, but just to show you the Al Gharafa Stadium, which is an existing stadium. On the left, you see an image of it. It's not my choice of color or my choice of architecture, but the scheme started, this is the colors of the country, the scheme started as the literal idea of a football and just cutting it off the top. So, of course, the inspiration is Bucky, and when we start looking at that, where do you start from? Because we actually got literally a football cut, as the first model from the architect. So you have to start thinking about, well, what inspired them? And they kept telling us about Bucky. So we looked at it, and just to give you a very basic idea about this is 200 meters, 240 meters. So it would swallow 10 Epcots. It's not a tiny thing, okay? And what happens is if you do the Bucky model and cut it off the top, which is diagram number A, you get something like 10,000 tons of steel, or 20,000 tons of steel. This is an empirical measure. When you do diagram B, where you start to reinforce it specifically with arches where you need, still sticking to all these rules, you get half the tonnage. And then when you go to diagram C, where it's a cell structure, now one of those cells is at least 4 times the size of Epcot. The tonnage goes to 11,000. And then you go to the diagram D, which goes right down to about 9,000 tons of steel. So if you were measuring, and that's the wrong thing to do, people, empirically we still measure cost with weight, but sadly that's the way it goes. So just measuring it and understanding it as a weight, that's 9,000 tons. So you're halving. If you work to Bucky's work and try to do this particular project, you wouldn't succeed. And when you get into the detail of diagram D, which is what we're building, you see all the efficiencies. So despite the fact that we've brutalized his thinking, the inspiration still starts from there. And actually there's a lot we've learned from the 120 years of thinking that we're now modeling and able to test in a very, very good way. And the details go on. So it's a hybrid shell in a way. The conclusion for me, I think that he was one of the first, in my opinion at least, to recognize that systems prosper when design, development, and research comes together, and when the more intellectual activities are integrated into production, assembly, and creation. It's just disappointing he didn't get to build much, but he was one of the first to realize that. My opinion is he inspired and continues to do so, but as an engineer, from my eyes, even though the geodesic is one of the most tested, I find his thinking very Socratic. We found very little evidence of tests, real tests in everything he did. There was a lot of writing, which is not the same thing as engineering or making something. There was a lot of patents, which in my opinion are unnecessary and a hindrance. So scientific culture, which is where I'm speaking from, is supposed to be expansive and confident at its roots, which is nothing that he was. In my opinion, he was quite secretive. Many ideas of the past will fail when analyzed. We find that regularly, the work of Dais, Nervi. When we try to model it, it doesn't work. The one good thing about Fuller is most of them work. They just work too well for the world today.
Now, thank you so much. The format, I have forgotten to say that there is a response in this case by Andrew Witt, that is an associate professor in practice at the GSD, and Ingrid Benston, that is a thesis student. And then after the responses and comments, we will open a few minutes to the public. Andrew, do you want to begin?
So I mean, two very, very different, but I think very complementary presentations. Really, fascinating material at the core, and I think it also sort of like points to a certain, obvious breadth in Bucky's thinking. And so, on some level, I'd like to actually begin with this question, almost like the cosmological significance of what he was trying to do and his sort of like world system approach to things. And in particular, the sort of, beginning with this geographic sort of perspective, there were two aspects of that I found kind of interesting. I mean, first, in particular, in the 60s and 70s, these moments when sort of systematic thinking about ecology was really becoming, sort of the sort of an intellectual focus du jour, I guess. The world game sort of set the stage for other kinds of, I guess, game theoretic approaches and understandings of resources. Like we think about World 3, we think of all of these other types of simulations which began to think about scarcity and the sort of felicitous resolution of that scarcity at a geographic scale. And so one of the things I'm curious about is in in that context, how did the world game actually play out? I mean, what was its relationship to these other types of simulation? Was it something that sort of, Bucky might have seen as game theoretic, or did he see it as sort of solving entirely different problems than these other types of simulations? Anyway, that was sort of like the first question. And then the second question was, when you look at the sort of cartographic approach to geodesic construction, Bucky is obviously, one in a very long line of people thinking about the projection of these polytopes onto spheres. And so we think about Kepler and his sort of like geographic mysticism in a way, and the sort of like nesting of those guys as a basis for those construction systems. The funny thing is, if you look at the sort of practice of cartography, by the time Bucky came around, it was much more sophisticated. You think about this process of triangulation of territory. Proto-computational models were already sort of in common sort of circulation, and we know that Bucky also used calculation techniques from geography, and that he must have been associating with people who actually had those types of more advanced, more inflected, more sort of like customized techniques of understanding inflected space. And so with those types of intelligent, sort of adaptive, sort of geometric techniques, why not embrace them fully? If we know that the world is not a perfect sphere, we know that even thinking about it at this cosmological level, it makes sense to begin to inflect structures in this more calibrated way. Why this oversight? I'm just kind of, I don't know. Those are two sort of points of discussion that I'm just kind of curious about.
Yeah,
but maybe I can have. I don't know if we have time to get into, but what is extraordinarily interesting to me, at least, is how he moves across different experiments. And of course, there's always a question between intuition and systematicity and testing, and is there too much testing? But for instance, in terms of the cartographic model, so in 1948, he publishes a centerfold of these pieces in Life magazine, where one can arrange them and rearrange them, right? And there's this famous photograph where he's on the floor rearranging the map, right? So it's no longer, and we know that in 1948 he's, of course, trying to figure out the Mercator distortion, he's trying to figure out the writing of the patterns, he's trying to figure out, so the capacity to move across these things, of course, has a feedback.
There's a fluidity between
Yes.
these projects.
Absolutely.
Very much so.
And so rather than seeing it as a kind of an empirical project on accuracy, it's actually almost the opposite, that it empowers one to rearrange things and to almost open them up for pattern recognition without knowing. And in that, there's some absolutely inefficient models, absolutely. But this idea, for me at least, that Dymaxion, this idea that you could rearrange your own map to discover different relationships that were at once received, right? You have an entire universe of cartography trying to become more accurate, and he just upends it. And in Life magazine, he gives you instructions. So every tile, if you turn it around, you cut it out, and it's got instructions, arrange at will, and then you can see 50 maps, you can see 100 maps, you can see 1,000 maps. It doesn't really, that to me, that kind of transversal thinking is really what is interesting, more than maybe some of the accuracy of the methodology.
It's interesting that although there's sort of these seeds of a combinatorial approach, that it's not exhaustive. You mentioned that only 6 of these Archimedean solids are selected, and was the selection of those particular approaches out of this universe, out of this combinatorial universe, what was it? Just, do you think it was a matter of expediency, or a matter of sort of like, I don't know, why select those particular elements in this wide universe, I guess?
Well, it's true what Hanif says, that he was incredibly secretive from digging the archives of Princeton. We learned that he would submit his students to a 2-week geodesic session before they could even enter the studio, and there is no record of what they were taught in that session. There's no record of what that was about, and there are records of waivers and disclaimers. You cannot take this with you. You cannot, So in that sense, we don't know.
But if I was, of course, I was being deliberately provocative with narrowing it down. But being thinking of what you asked us to think about, which is the future, there is without any doubt, in my mind at least, that he was one of the greatest thinkers, and people like him are beginning to come back, whereby you do have across the disciplines, cartography, across scales, across ways of thinking, rather than being multidisciplinary, where you do little bits of everything badly. He was actually pretty good at something. That wasn't engineering, as in structural engineering, but he was a pretty good thinker, and able to take the best bits out of all of these disciplines and make something out of it. And that is certainly a lesson that, as an engineer, I try to encourage people to think about, because you cannot just have one eye, invent the wheel, and then live off that for the rest of your life. So he did continually. Also, one of the other fantastic things I feel he did was self-promote, which is another rare thing in people of that generation. Which there is nothing wrong with that. Today we have too many of those, but at that time, I think it's helped us, because some of that work has been very inspiring. So, for me, that would be kind of half an answer to what you're saying.
I mean, one of the other things that I always found amazing about Bucky's approach was the degree to which these very sort of like initially sort of modest experiments can be sort of like aggregated into something that has some significance. Yeah. And so I was actually kind of struck that about sort of the lack of sort of analytic confirmation in a way about that process. But I think there's something to learn about that. There's something to learn today about the sort of like beginning with these sort of like modest experiments and creating a sort of framework for extrapolation or a platform for extrapolation. I mean, what do you think accounted for the success of such a modest process when today I think there's a little bit of anxiety about thinking, we have to immediately think about the structural possibilities of this. And I mean, like how was he able to get away with so much in a way without?
Can I be honest?
Yeah, please, yeah.
He didn't have cost consultants, project managers, people who kill design. So in my opinion, he tended to, I'm sorry if I offend anyone, but he had the freedom of not having to worry about what I have to worry about, how much tonnage there is in this object. Even though there's a moment at which I don't want to be seen doing it. It's ugly, But the point was that I think, in his generation and the way he convinced people, he managed to survive through that because he didn't have all those other issues that we're having to face today. And in some instances, quite rightly, because we have lost our disciplines and been exuberant. So sometimes we see the experiments with what you call a modest thing, for the sake of the experiment that become very ugly very quickly, or is just proliferated for the sake of the tool or by the tool, whichever. And I think he didn't have that luxury. So he had to play very carefully his cards. That's how I'm imagining it. I don't know if that's the case. Mm-hmm. Whereas today, I think we have far too much to do, far too many things we can do, and it spoils us. It does, yeah. So choosing what's good being ugly or least weight, whichever, and how do you take that to the next level? And when we make those decisions, in any case, they're taken away by the other disciplines, which is the people who count.
Yeah, I mean, I feel like on some level there's also something to be learned about the criteria for design choice, which Fuller, I think, very sort of like strictly and rigorously brought to each of these projects. The Dymaxion maps, the domes, everything was essentially about not only a quantitative criteria for that performance, but a sort of very democratic, qualitative, sort of like inclusive criteria for success, which I don't know, I always found very, very compelling.
That's something that's particularly interesting to me about Fuller's work, is that he was so much of a philosopher, and that he had these really democratic ideals that he was embedding into all of his work, and it was really guided by his ideas about like a deep structure of the universe, and like very totalizing. And so I'm actually interested in compiling your work, like what if there will be some sort of, I don't know, theoretical message, or what people will be able to take from this compilation.
I mean, there is which we didn't have time to go over today, but there's an immense discursive dimension to the synergetics dictionary and to synergetics in general, where he develops these concepts, writes about them, writes definitions. And for Fuller, patents were expansive. I mean, although they were secretive, they were expansive. He said, this is the best, this is what I know. If someone can come and challenge it, then we build knowledge together. It's an open knowledge base that keeps accruing. So he would reference, you know, in the same way the synergetics dictionary is a network of definitions that overlap. The patents are made of synergetic concepts that are a network of relationships, right? So there's a vast body of work there that obviously speaks about the meaning of these lines, right? It's not just lines of structure, but actually, you know, a deep, you know, organicist project, right? And of course, we are interested, or I'm interested in both facets, definitely. It's incredible if, and I encourage everybody to do it, to read some of the language in the patents, because he includes extraordinary pieces of text that define the universe, right? And patents it, right? I mean, it's part of the body of a patent. So these definitions are not, you know, they begin empirically, right? The sphere subdivided by a number of whatever, and then they start to zoom out and start to really expand outwards. So definitely, yeah.
Is this research available? Is in internet or in
So,
a book, or what are you doing with this?
Well, right now we have a portal, which is the sphericalaTlas.com, where we have all of the, you know, all of the prototypes, and you can trace them by grids and projections. But we also have the body of the patents, and then from the patents, we get to the synergetics dictionary. The synergetics dictionary is extraordinary. It's this huge volume where Applewhite, which collaborated with Fuller, would clip every concept, word, term, definition, claim into note cards and assemble them in a network chronologically, alphabetically, and they're interconnected.
A beautiful mind style.
And so, right, and then this becomes, these are, so the patents are folded into that. So right now in the portal we have the patents, and then from the patents you can trace the synergetics dictionary terms, and then you can trace the bibliography. You can really trace networks of thinking in real time, and we have a growing glossary that's going to be integrated. Now the portal is just a template until we are able to work on the final publication for sure. But it's definitely both.
Both is yours too?
Yeah, no, it's going to be in there. But what we're looking for is a small amount of funding so we can test more. You know?
Yes.
It's all spectrum.
We'd
We'd like to test a lot more.
Yeah, let's open to the public, please.
So thank you. You mentioned, this is great, and you mentioned about meaning, the internal processing.
Can you wait a moment? Please bring the mic. Sorry for this.
This is going to be a vague question, but you talked about meaning and moving beyond the structure, the surface structure, the physical structure. So I'm wondering what this implies about phenomenology and the development of human consciousness and the role, the interface between those two. Any work on that?
So, well, Fuller is vast, and as of right now, we are still in the synergetics dictionary as entered from the definitions of the patents. So, because you know his writings are again this expansive. He writes a text and then republishes as an expanded version of a text and then republishes, and so not yet specifically in this more abstract
Or less
realm or
Less
yeah.
I mean, I would say that actually from a sort of like philosophical framework, maybe the phenomenological questions are a little bit open, but the ethical questions I think are very much there. I mean,
Yes.
these were sort of priorities in which Fuller, or these were projects in which Fuller was trying to elevate a certain level of human dignity, and I think those kinds of concepts were sort of pervasive.
Sure.
And so, although he's thinking about it, I think at an abstract level, it was nevertheless, a sort of philosophical project in that sense. It's the way I perceive it.
Sure.
Yeah, exactly. There was a sort of ambition about that, which I think had to do with sort of fun. I mean, it's sort of like I don't know, what he saw as these sort of like essential American qualities in a way, which I thought was really sort of interesting.
Sure. I mean, right now we are also working on a small publication that deals with this design science decade. So in 1963, challenges the Architects Union, International Architects Union, to write a 10-year brief to what he calls a turning point, right? We have 100% of the Earth's resources serving 44% of its population, and he maps out population growths, and so that is beginning to, he was very clear about these kind of inequities and political questions.
Something that's funny, something that's just so funny to me, though, about that sort of project for humanity is that it comes from, it stems from his sort of like preconceived notions of the structure of the universe, and then he had these ideas about the structure, and so like in many ways, I think better. I mean, it's sort of like this narrow-mindedness, which maybe Hanif was referring to earlier, in maybe different ways of combining humans together to best maximize the use of efficiency of energy systems and that kind of thing. I mean, everybody's getting their little dome house, and I find that like very.
He was playing the world game in God mode.
Thank you very much. I'm curious, you mentioned you started off talking about pattern thinking. If you had a 10-year-old, I have a 9-year-old.
I have an 8-year-old.
Okay, good. And Bucky is eternally, relevant, right? So what would you want would you say 8? What would you want your 8-year-old to walk away with, to know about pattern thinking?
Well, he has, in this energetics dictionary, and then there are abridged versions of it. So Garland publishes the full set, and then you can get abridged versions. He has a path for a child. I mean, Fuller had a lifelong commitment to education at every level, from elementary school all the way up. This design science decade was challenging departments of architecture, actually, to work together. Is that all of your research is all disparate, but the military complex works consolidated, so why don't we all work consolidated and try to, livingry versus weaponry and these kind of terms. But he does have a path to enter these concepts for a child that one can follow. And of course, these concepts, he shows the jitterbug surrounded by children in classrooms, and he's very committed. And towards the end of his life, he does write a number of children's books. That some of them are tetra scrolls that unfold the maps and ways to crystallize our relationship to the environment as understood by a child. So it's a very meaningful question to him.
I want to know your answer.
Yeah.
Pattern thinking. Very simply, I'm 10. Tell me, without a lot of, just give me a really simple, what do you want me to know?
Well, I guess, okay. So if you go back to that to him de-inflating the globe or hugging it, we don't know yet. Trying to understand the globe, trying to understand your environment. I mean, I think that the basis of what he was constantly returning to is what's your relationship to a larger collective. And what patterns of what you do, the patterns of what you do have an impact. Across, so he's constantly, so with something as abstract as the jitterbug, which is trying to convey to a child that actually all polyhedral are connected, right, mathematically, with a kind of a level of complexity that's really high. It's actually, you do it. You turn the dials, right? And we've seen models of the jitterbug that are the size of, where a child can get in and actually rotate and begin to understand geometry, not as this abstract thing, but as related to the body and what the body does as a pattern. So that's what I would tell my 8-year-old.
I had the fortune of doing that. I was invited to a girls' school, 10 years old girls. I have 12-year-old, and they asked us to try and teach them something. And what we got them to do is make out of polythene, small, and took a bowl to the school. And in one day, they were able to make a small tent using some of these geometries. And then the teacher was able to connect it to nature. All the nature models that connect to what he did with the geodesic. So I've actually seen it in action, how quickly they understand the third dimensions for these patterns.
We are running out of time. But I will open to one or two more questions. I want to make an intervention thinking as an architect. I think, for two things. One is pattern. I think that pattern is completely essential to design. It's the basic. It's like rhythm or melody for music. It's brutally important. And for every creative thing that has any relationship with drawing, and even the most automatic drawing. And the second is about, as an architect, looking at the obsessions of Bucky Fuller, I cannot still understand why he insisted in the dome. Honestly, every architect knows that a dome is not a dome. From a long time ago, and the treatises. No, it's more a paraboloid or whatever, and it's, when you say the inefficiencies of his work, I think are basically geometric. This obsession with Platonic solids. I understand the obsession, but at the same time, it's so anti-structural, and it was. Everyone knowing the basics of graphic statics knows that it doesn't work.
No, but my view is it's that I wouldn't hug something else, but I would hug the dome.
Good point. Last questions, please. Yes.
So you've been talking a lot about the importance of Bucky's cosmology, and it was somehow implicit in almost everything he did. But you mentioned, I think, that he tended to think of everything, you used the word heavenly, as heavenly. And I was wondering what you meant by that.
I think I'm not sure, but you have to have been kind of blind to the everything to be able to produce what he did. So in my case, what I meant by that was I knew at a very early age that load is not an even thing. Gravity across the world, even though we use 9.81, most of the best engineers know it varies, and there's a micro variation in it, and topography affects it. But if you start to consider all those things and make them slightly more twisted, and it's not ideal, maybe I should have used the word ideology. He was ideal about loads and about everything he made. He thought it was all very nice and nobody was there to get you, but the eccentric load is there to get a structure. And the earthquake is there to actually challenge heavenliness in the way we work. That's what I meant by it.
Also, I think early in his life, he was a sailor as a child, right?
Sure.
And
He understood nature.
his whole life,
better.
right? And I think Tensegrity came to him while he was also a very isolated child at some level because of his visual issues, but that it was looking at the heavens, that the whole concept of tensegrity, the lines of vision, but the line, I just remember something vaguely about that.
Many layers of meaning, and some of these have been constructed after the fact, but his boat was named Intuition. And he describes sailing as this kind of intuitive conversation with the wind and the forces, and without having to understand them fully.
Right, and even the structure of the boat, I think,
Yes,
the
sure,
sails
sure.
and all of that was a kind of microcosm. So.
Well, thank you so much. I think all of us have enjoyed every single second of these interventions. Thank you so much.
Thank you very much.